Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss quasi-static, quasi-static expansions of an ideal gas. Quasi-static expansions of an ideal gas. So you know what is ideal gas. We've already discussed it. A gas which obeys this equation, PV is equal to nRT. An additional restriction on it is that its internal energy is function of temperature only. These things you need to keep in mind. And another thing, I have already discussed that. I'm just revising it in order to continue smoothly. Quasi-static process. Quasi-static process in which piston moves infinitely slow with zero acceleration when gas expands against the piston and does work on surroundings, or is compressed and surroundings do work on the gas. So we are doing process quasi-statically, or we say quasi-statically, right? Now we have already said it that work done if we have some container and it has a certain piston, right? Now there is gas inside this container. Now if this piston moves, right, through distance dx, then if A is the area of the piston, then d change in volume of the gas is A dx, and work done by the gas when piston moves, gas expands, work done by the gas on the surroundings on the piston is PdV, where P is the pressure in the gas. P is pressure. This much you know. Now, if gas moves from some volume V1 to volume V2, and we know this will be shown in the PV diagram like this. Gas will have some pressure P and volume V1, then it will move some other pressure, the same pressure, but volume V2. That means process is occurring at constant pressure. Then our total work done by the gas will be integral dW from V1 to V2. Then we will put PdV here, V1 to V2. P can be taken outside because we are saying that pressure of the gas stays constant. And inside integral I will have dV, V1 to V2. It will simply become P times V2 minus V1. So this is the work done by the gas, during an expansion, quasi-static expansion, when the pressure of the gas stays constant. Now such processes are called, they have a name, isobaric processes. So isobaric process is that process during which the pressure of the system stays constant. So for isobaric process, for all isobaric quasi-static expansion of an ideal gas, work done by the gas is P times V2 by V1, where P is the pressure of the gas, V2 is the final volume, V1 is the initial volume. And we know this work, right? This is V1 in the PV diagram, this is V2 in the PV diagram, and this work done by this gas will be represented by this area, right? Now there are other two processes which are important, and we want to find the expressions for the work done by the gas for those two processes. This was for isobaric process. Other processes, quasi-static, isothermal, expansion of an ideal gas, right? Quasi-static, isothermal expansion of an ideal gas. First, what is isothermal process? Isothermal process is that process during which the temperature of the system remains constant, right? The process during which temperature of the system stays constant is called isothermal process. Now for such process, we want to find the expression for work done by an ideal gas. Before that, I want to tell you about heat reservoir. What is heat reservoir? When we do some process, for example, it is my system, this is my gas, this is my system. Now I want to do some process with it at constant temperature, that means isothermally. Then what we do, we bring our system in thermal contact with another system. This system is called heat reservoir. So you have to remember, whenever we do some process with our gas or system at constant temperature, or we say this process is being done isothermally, our system is in thermal contact with heat reservoir, which is another system. Now, heat reservoir is a system which ideally has infinite heat capacity, so that if you take any amount of heat from the system, its temperature will not drop, and if you put any amount of heat into the system, its temperature will not increase. Now, in practice, it will have a large heat capacity, right? So when we do some process isothermally, you need to keep this thing in mind, that your system is in thermal equilibrium with another system, heat reservoir, whose heat capacity is large and its temperature is same as that of the system, right? Then now we want to find the expression for the work done by the gas if it expands against the piston isothermally from volume V1 to V2. First, I draw PV diagram. So I have some ideal gas at with in state P1 V1. I want to take this system to another state P2 V2 along a path along which the temperature of the gas remains constant. So this is my constant T. T stands for temperature. Constant T path. This constant T path, and you know this area under the curve will be my work done. This area is the work. This is work, right? And this constant temperature path has a name. It is called isotherm. What is isotherm? It is that part in the PV diagram along which the temperature of the gas stays constant. I want to calculate the expression for this work. If my ideal gas goes isothermally from state P1 V1 to state P2 V2, what is the work done by the gas? I know this is this area, but what is its expression? We know for an ideal gas, PV is equal to nRT. Now, since when we take the gas, its amount is constant during the expansion, R is universal gas constant and T is also constant. That means this whole thing is constant. That means PV product is constant. We need to remember PV product is constant. So along this isotherm, product of pressure and volume is constant. Now, such a curve has a name. This curve is called hyperbola. So you need to remember this. Then when gas expands isothermally, then the shape of the curve along which it moves, which has name of isotherm, is hyperbola, and the product of pressure and volume along this curve is same everywhere. Temperature is same everywhere. Now we move to work. Now small work done by the gas is PdV, right? Now P can be replaced by nRT by V, right? P is from this equation nRT by V. So I substituted instead of P nRT by V. Now the total work done by the gas when it moves from volume V1 to volume V2 is simply PdV V1 to V2. For PdV, I write nRT by V dV V1 to V2. Now since n is constant, R is constant, and the process is taking place at constant temperature, T is also constant. So I will have nRT outside the integral, and it will be dV over V V1 to V2, right? So when I solve it, it is nRT. Its integration will be ln V, natural logarithm of V. Then you put the limits, ln V minus ln V1, ln V2 minus ln V1. Then use the rule log m minus log n is log m by n. So it will be ln of V2 by V1. This is my expression. So you need to remember, I encircle it. So this is your expression. So you need to remember, if an ideal gas containing n number of moles expands isothermally against the surroundings, against the piston, at absolute temperature T from volume V1 to V2, then the work done by the gas is given by nRT ln of V2 by V1. So next thing, if we apply first law of thermodynamics to this gas, now from first law of thermodynamics, first law of thermodynamics says heat put into the system is equal to change work done by the gas plus change in internal energy of the system, right? We apply to this ideal gas. Remember, as we said, U is the function of temperature only for an ideal gas. And during this isothermal expansion, temperature of the gas stays constant. That means its internal energy stays constant. That means dU is 0. Therefore, dQ is dW. That means for an ideal gas, during an isothermal expansion, work done by the gas is equal to heat put into the gas. You need to remember this. That means this area is not only work, it is also heat absorbed by the gas from heat reservoir, because it is absorbing heat from the heat reservoir because it is in thermal contact with it. So remember, this is not only the work, it is also heat absorbed by the gas from heat reservoir, right? Then we have next thing, quasi-static, quasi-static adiabatic expansion of an ideal gas. Now another process we take into consideration. We discussed isobaric process, we discussed isothermal process. Now I want to discuss adiabatic process. You already know adiabatic process is that process in which no heat enters the system from surroundings and no heat leaves the system to the surroundings. That means Q is 0 in first law of thermodynamics. No heat exchange takes place between the system and the surroundings. And how is that possible? Our system will be adiabatically isolated from the surroundings. Now, if I apply first law, from first law, again from first law of thermodynamics, first law of thermodynamics says dq is equal to du plus w, or dw. W is work done by the gas, right? Now, for adiabatic process, dq is 0. That means W is minus du. This is important. That means in adiabatic process, work done by the gas, I specify it here, work done by the gas, by the ideal gas, work done by the gas is equal to decrease in internal energy of the gas. We know internal energy of an ideal gas is function of temperature only. That means if its internal energy decreases, its temperature decreases. So this is important, that during an adiabatic expansion of an ideal gas, T decreases, right? During isothermal process, expansion temperature stays constant, but during adiabatic expansion of an ideal gas, its temperature decreases. Because of that, what happens? We know PV is equal to nRT, right? Now, when we take our PV diagram, when gas expands, volume increases, P decreases. Now, if it is state 1, this is state 2. Now, if gas expands isothermally, T is constant. Now, volume increases, pressure has to decrease, right? Now, so there in isothermal expansion of an ideal gas, there is only one reason for pressure to decrease, that is the increase in volume. But for an adiabatic expansion, not only volume increases, temperature also decreases. I repeat, for an adiabatic expansion, not only temperature increases, but also volume increases, but temperature also decreases. So there are two reasons for pressure to decrease. Because of this, along the adiabatic path is more steeper than isothermal path. That means that in adiabatic expansion, pressure decreases more rapidly than isothermal expansion. I will now want to calculate the expression for the work done by an ideal gas during an adiabatic expansion. First, I will draw a PV diagram. Then I will find the expression for the work. So my PV diagram is like this. This is P, this is V. Now I want to take the ideal gas from state P1, V1 to state P2, V2, right? Along this adiabatic path, this be my adiabatic, right? So this is my adiabatic, adiabatic. Let me fix this pen. This. Fix this first. Okay, so this is my adiabatic path, right? So this area under this curve is my work. This is my work which I have to calculate, right? We know here temperature will be large, here temperature will be less, because along adiabatic path temperature decreases when gas expands. So let temperature here be T1, temperature here be T2, right? So there will be an isotherm, because there will be an isotherm corresponding to every temperature. There will be an isotherm corresponding to T1 and isotherm corresponding to T2. So let this be isotherm for T2, and there will be an isotherm for T1. I just want to make the comparison. See, this was isothermal expansion, but because of decrease in temperature, adiabatic path is steeper. This curve is away from this, right? Now we want to find the expression for work. We start this way. We said from first law of thermodynamics, dq is du plus pdv. It is work done by the gas, which is pdv. Now it is 0 because dq is 0. Also, we know from our previous lectures that Cv, heat capacity at constant volume, is du by dt, right? Cv is du by dt. That means du is Cv dt. Cv is heat capacity at constant volume, right? So I substitute it here. Instead of du, I can write Cv dt. So my equation becomes Cv dt plus pdv is 0. Let this be my first. I have replaced du by Cv dt. Then I have plus pdv. This is 0 because dq is 0. This is my first equation. Now, next what I do, for an ideal gas, change the color, PV is nRT. PV is nRT. So I differentiate this equation. I will get PdV plus VdP is equal to nR dt, right? PdV plus VdP plus is equal to nR dt. Now I multiply this equation on both sides by Cv. So multiplying on both sides by Cv, heat capacity at constant volume, it will become Cv PdV plus Cv VdP is equal to nR Cv dt, right? nR Cv dt. Now what is Cv dt from first? Yes, Cv dt is what? Minus pdv. Cv dt is minus pdv. So I will use it here. I will get Cv pdv plus Cv VdP is nR Instead of CVDT, I will write minus PdV using first. My first was CVDT is minus PdV. So I will replace CVDT by minus PdV. I rearrange. I will take this term to left hand side. It will become plus NR PdV. Then PdV can be taken as common. I will get CV plus NR times PdV plus CV VdP is 0. It is simple. I have taken this term to left hand side. It will here become plus NR PdV. So these are these two terms, CV PdV plus NR PdV, right? What is CV plus NR? Now, Cp, heat capacity at constant pressure, is CV plus NR for an ideal gas. That means I can replace this CV plus NR by Cp. What's my equation now? Cp, here I write Cp, PdV, Cp PdV, here I write Cp, then I have PdV plus Cv VdP plus Cv VdP is equal to 0, right? Cv VdP is my equation. Then what I do, I divide this whole thing, dividing on both sides by Cv PV, right? Why I am doing this? Actually, first I want to find the relationship between pressure and volume for adiabatic process in order to calculate the work done by the gas. So when I do, I divide this by CV PV, I will get, this is, I will write directly, I will get Cp by Cv dV by V plus dP by P is equal to 0, right? Or I write gamma dV by V plus dP by P is 0, where gamma is denoting Cp by Cv, the ratio of heat capacities, right? What I have done, I have divided here by Cv Pv. So here P will go, Cp by Cv will remain, and dV by V will remain. Right hand side will be 0. Yet Cv and V will cancel, dP by P will remain. Then I replace it Cp by Cv by gamma. So my relation is gamma dV by V plus dP by P is 0, right? Then what I do, I integrate this equation. Next is integrating. We get, when I integrate, I will get gamma natural logarithm of V plus ln P is equal to constant, right? Gamma ln V plus ln P is equal to constant. Simple. Integration of 0 is constant. This will become ln P. This will become ln V, and gamma will be multiplier, right? Then I can write it ln of P V raised power gamma. I simply use here, this will be ln V raised power gamma, then plus ln P, log M plus log N is log Mn, So that when I use, it will be ln PV raised per gamma is some constant, or PV raised per gamma is constant. And this constant I name as K. So I have obtained the relationship between pressure and volume for an adiabatic process. This is PV raised per gamma is constant, and that constant I name as K. Now I move to work. Work done is PdV, right? Now P I replace by K by V raised per gamma, K by V raised per gamma, because PV raised per gamma is constant. That means implies P is K by V raised per gamma. So I have replaced P by K by V raised per gamma. Or I can write it K V raised per minus gamma dV, right? So next, what I do, I integrate the work done by an ideal gas during an adiabatic expansion is integral dW V1 to V2, which is V1 to V2 K V raised per minus gamma dV. K V raised per minus gamma dV. I write it directly. When you integrate it, it will be K by 1 minus gamma times V2 raised power 1 minus gamma minus V1 raised power 1 minus gamma. Remember, gamma is Cp by Cv. Let me use this color. This is my relation. So if a gas expands from volume V1 to V2, ideal gas expands from volume V1 to V2, right? Then adiabatically, then work done from volume V1 to V2, then this is the expression for work done by the gas. K by 1 minus gamma times V2 raised power 1 minus gamma minus V1 raised power 1 minus gamma. Gamma is Cp by Cv, and K is, what's K? dV raised power gamma, right? I will give you homework problem. Tell you this color. Homework is 1 mole of nitrogen expands isothermally at 20 degrees Celsius from a volume of 10 to 20 liters, assuming nitrogen to be an ideal gas. How much heat, how much heat must be supplied the temperature to keep the temperature of the gas from dropping. I repeat the question. 1 mole of nitrogen expands isothermally at 20 degrees Celsius from a volume of 10 to 20 liter. Assuming nitrogen to be an ideal gas, how much heat must be supplied to keep the temperature of the gas from dropping? So do your homework. That's all for today. Thank you. God bless you. Assalamu alaikum.